The last part of the chapter deals with organic chemistry. Organic chemistry refers to the chemistry of carbon-based compounds. Now, when you go on to big boy school, there will be entire semesters worth of classes that you can take just on organic chemistry. You are not going to be an expert by any means, but I do want to give you an introduction because a lot of the information that we'll talk about later in the semester with the consumer chemistry actually deals with some different organic chemistry concepts. So let's try it. So, like I said, organic chemistry is the chemistry of carbon-based compounds. Now, it was originally called organic because they believed that these compounds could only come from living things, but then they were able to synthesize these in the labs. So now they're just referring to carbon-based compounds. We're going to start by talking about a hydrocarbon. A hydrocarbon is just carbon and hydrogen. That's it. No other elements are going to be involved. But it's amazing to see how many different arrangements that you can do with these carbon-based compounds. Now we're going to start with what are called alkanes. An alkane is a hydrocarbon, so just carbon and hydrogen. And we're only going to have single bonds, so no double bonds or triple bonds yet. Carbon is notorious for doing double and triple bonds, but not just yet. We're only going to look at single bonds. And at the very bottom, it uses the term isomer. So isomer, it says it's the same molecular formula, so it has the same number of carbons and the same number of hydrogens, but we've arranged them differently. Well, I'm going to give you an example, but I'm only going to look at just a carbon. So let's say that we have 4 carbons. So we could put the 4 carbons. Let me hold on to this. 1, 2, 3, 4 in a row. Now around those carbons, we're going to see some hydrogens filling in. We could take those carbons and we could put 3 in a row and then make one into a branch. So same number of carbons, same number of hydrogen, but it's got a different molecular arrangement, a different structure. So that's why it's an isomer. With this one, there's actually one other. Oh, no, I was wrong. There are no other possibilities. I can't put it down on the top because that's the same as this one. Can't do the ends. It's the same as the beginning. All right, just 2 isomers for 4 carbons. If you have 5 carbons, I believe there's 3 isomers. I believe 4. It gets more complicated as you add numbers of carbons in there. When you name an alkane or any type of organic compound, the name is based on the number of carbon in the longest chain. So this slide just goes through some of those basic names. So if you have 1 carbon, it's called methane. Methane is natural gas. So my husband taught my kids that when they pass gas, there's some methane in it. There's a big study about cows and how much methane they produce. So my kids, instead of saying that they fart, they will giggle and say CH4. So just a warning, if you're around my kids and they start giggling and saying CH4, be careful. Be very, very careful. Now, as you add carbons onto there, the name changes. That prefix, the first part. Eth means 2, so ethane has 2 carbons in a row. The ane part at the end just means it's an alkane. So if we change it from being just single bonds to adding double or triple, that ending would actually change. It would change to an alkene or an alkyne. But the first part is what we're worried about right now. And again, it represents the number of carbon in that chain. Prop means 3, so propane, when you grill your steaks or your hamburgers, you use propane gas. That means that the molecule has 3 carbons that are attached to one another. Butane, so your cigarette lighters have 4. Pentane, 5. Hexane, heptane, octane, nonane, and decane. We're only going to go to 10. You'll notice that these prefixes are similar to the ones that we learned about earlier for what was it, the covalent naming, except for the first four. So instead of saying mono, di, tri, tetra, in organic chemistry, we use methyl, ethyl, propyl, and butyl. It's just the way that it goes. Now, this particular slide is looking at what happens when you have an entire chain. What we're going to end up with is off of that chain, there's going to be some side groups. And those side groups use the same prefixes to indicate how many carbons there are. Again, organic chemistry can get pretty fun. So let's learn some more. There are many different ways that you can indicate or draw the compound that you're looking at. So that's what this slide is going to look at, some of the differences between them. The molecular formula just gives the mole ratio, so it tells you how many atoms of each element there are, but it doesn't say anything about how they're bonded to one another. So an example of a molecular formula would be C4H10. You know that there's 4 carbons and there's 10 hydrogen, but that's all that you know. The Lewis structure is going to show more about the different isomers. It shows the actual bonds between the atoms. So sometimes this will be called an expanded view also. So here I'm going to say, well, there's 4 carbons attached to one another. And off of those carbons, we're going to put some hydrogens. And this is showing each individual bond. Because it turns out with carbon, if you're to draw the Lewis symbol, it has 4 dots. It wants to form 4 bonds. So we can show how the carbon is going to form bonds with other carbons or with hydrogens. But there's going to be 4 things surrounding, 4 bonds surrounding each of those carbons. Now, it takes a little while to actually draw all of those carbons and all of those hydrogens out. So you could also do what's called a condensed structural formula. And on this one, we're going to say, okay, I've got a carbon and there's 3 hydrogens around it. That carbon's attached to another carbon, which has 2 hydrogens. That carbon's attached to another carbon with 2 hydrogens. And that carbon is attached to a carbon with 3 hydrogens around it. These 2 structures are actually identical to one another. I know it doesn't look like that right now, and it takes a long time to train your brain to realize that they're the same. We just wrote them a little bit different. Now, we can go even further. If you want to write it in a very, very simplistic manner, just dealing with organic chemistry, we can draw little lines. The little lines, the corner end of the lines indicate that's where a carbon atom is. And we're not even going to put in the hydrogen. They're just assumed to be there. Now, this is called a line drawing. Line drawing, because literally you're just drawing lines. Just this little thing right here means exactly the same as the 2, or actually 3 that I'd drawn before. So remember, the corners are your carbons. So I have 1, 2, 3, 4 carbons. And then you could imagine how many hydrogen that it needs. So the terminal carbons need 3 hydrogen. The interior carbons need 2 hydrogen. It's going to give you that same molecular formula, C4H10. So all of these kind of mean the same thing. Now, that's not the only way that you could draw C4H10. We actually drew another example earlier. So let's look at that other isomer. Let's say we have 3 carbons in a row with a carbon that's a branch. So here, right here in the center, we're going to draw this one. Now on this one, we're going to draw the hydrogens. I know some of them are going to be obscured for you. It'll be okay. And some of my H's don't look like H's. It happens. Now if you counted up the H's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, There's 10 hydrogen, there are 4 carbon. It's the same molecular formula, but it's an isomer. How we wrote that structure is different. It will have different properties. We also have to give it a different name. Oh, we get to learn about naming on the next slide. Now, if I wanted to draw this in the condensed view, I'd have CH3, CH, CH3. Now, if that center carbon, there's another CH3 down here. If I was to draw it with the line, 1, 2, 3, off the second one, there's a side branch with another carbon. So just different ways to show the same structure. A space filling model, that is using the little, earlier I had shown an example of water. It had a little red ball and 2 little white balls, and they were little magnetic ones that were kind of fun to play with. That's a space filling model. It gives you a much better indication of actual size in relationship to one another, but I can't draw those, so I'm not even going to attempt it. Well, let's look at the next slide and talk a little bit about naming. Now, naming organic compounds can get pretty complicated. I'm not worried that you can name really complex ones, but I do want you to start learning about what those names mean. Now, the group that came up with this naming technique is the IUPAC. We've seen that name before. That's the International Union of Pure and Applied Chemists. It's a bunch of chemistry nerds get together and talk about these things. When they came up with this particular naming technique, they said, okay, the first thing we're going to do is identify the longest continuous chain. So sometimes it's like a maze trying to figure out what the longest continuous chain is. It doesn't have to be in a straight line. It can zigzag around, but we want to see how many carbon are in that longest chain. We're going to identify any side groups. So are there any branches off of that chain? And we actually number the carbons, so your side chain gets the lowest number possible. Let's go on. It says indicate total number of each set of mutually identical groups with a prefix. That means if you have 2 side chains that had the same number of carbons, so you had 2 methyl groups, you call it dimethyl or trimethyl or dipropyl or whatever the case might be. You give each group its individual location number, so we number the original chain of carbons, and we're going to say where each of those side groups is actually located. And we separate numbers by commas and separate numbers from letters by a hyphen. So on the last slide, we have looked at 2 different isomers. We looked at one that was just 4 carbons. Now, to keep it really simplistic, I'm just going to draw the carbons and none of the hydrogens. Now on this one, it's all in one chain. It's all straight across. So we could number them 1, 2, 3, 4. Now you actually have to look to see if you should number it from left to right or right to left. On this one, it makes no difference because there's no side groups to be able to try to look at. So 4 carbon in a chain, that prefix is bute. Because this is an alkane, meaning it's only single bonds with just carbon and hydrogen, we put the ending ane, butane. Now the other example that we have looked at, still with 4 carbons, but this one had a branch, looks something like this. Now if we try to find the longest chain, say, oh, it's got 3 carbon in its longest chain. Let's number it. Now on this one, it doesn't matter if you go left to right or right to left. The side group, either way, is off of carbon number 2. Now that side group right here, there's just 1 carbon in there, and 1 carbon we refer to as methyl. So when we name this, we would say on carbon number 2, there is a methyl group. The entire chain has 3. 3 is propane. So ane refers to an alkane, only single bonds hydrocarbon. Prop indicates the number of carbons in the longest chain. Methyl is a And that side group is located on the second carbon from the longest chain. You'll see some more examples. So let's try a couple of more compounds, organic compounds, to look at the naming. So let's see here. Again, for simplicity, I'm only going to just draw carbons. I'm not going to draw any of the hydrogens. Okay, that looks like a good one. So the first thing you're going to do is figure out where your longest chain is. So if I look, this one's actually going straight across. And in that longest chain, there's 1, 2, 3, 4, 5, 6, 7 carbon. Now I need to number those carbons, but I want to make sure that the numbering makes my side chains have the lowest number possible. On this one, the side chains are both on number 3, so it does not make a difference. Okay. The next thing I'm going to do is look at each of my side groups, and I'm going to try to identify how many carbon are in each side group. So my first side group right here, well, that just has 1 carbon on it. So that is a methyl group. The next side group, there we go. Well, this has 2 carbons in the chain, so we call that ethyl. And then my third side group, it just has 1 carbon. What was 1 carbon again? Oh yeah, methyl. Now comes the fun part. We get to try to name this. And, you know, again, I didn't come up with the naming techniques. I just use them. What they say is that these side groups you're going to identify first, but you're going to identify them in alphabetical order. That's why I like to put a little letter down to say what side group it is. So which comes first, M or E? Oh, yes, that would be E. Now that ethyl group is on number 4. So on the 4th carbon, there is an ethyl group. On number 3 and on number 5, we have methyl groups. Now, to really emphasize the fact that there are 2 methyl groups that we're looking at, they call it dimethyl. There's 2 methyl groups, 2 separate methyl groups. And then the longest chain had 7, so we call it heptane. 4-ethyl 3,5-dimethyl heptane. That's kind of crazy, isn't it? All right, so let me try another one. Okay, this one's good. Look at it just a minute and see what you can find out. First thing we're going to do, find your longest chain. Now, a lot of people would immediately say, oh, there's longest chain, but it's not in this case. Longest chain actually goes down here. That's kind of tricky, isn't it? If I number it, 1, 2, 3, 4, 5, 6, 7. Otherwise, it would have just had 5. Remember, they can zigzag back and forth. For the side groups, well, this one just has 1 carbon. That's a methyl. This one has 1 carbon. It's methyl. So when I name it on number 2 and number 4, we have methyl groups because there's 2 methyl groups. It's dimethyl. My longest chain has 7. So 7 is heptane. So it's just a really brief introduction. Again, I do not expect you to be experts at naming organic compounds, but I would like for you to start learning those rules. So it's time for a couple of end of chapter. Yes, we are at the end of the chapter questions. This one says 2,2-dimethylpropane contains 3 carbon atoms. Ooh, so you have to remember how to draw this or to know a little bit about organic chemistry. Now, I'd always drawn the structure and then ask you to name it. If you're given the name, it's actually a little bit easier to draw the structure. So this one, we read them backwards. It has propane. Propane has 3 carbons. I can't draw on this slide, so in your mind, draw 3 carbons. And then off of those 3 carbons, on the second one, on the middle one, there are 2 methyl groups. And methyl just means 1 carbon. So you could draw 1 carbon going up and 1 carbon going down. Now, how many carbons total are in that structure? Is it 3? No, it's not. Propane has 3, but this particular structure had some side chains, and that side chain made it to where there were 5 total carbons. All right, so here's a question that deals with drawing the different structures, not necessarily being able to name them, so yay. It says, what type of symbolism will show all of the bonds between the atoms? And it gives you some choices, a molecular formula, a Lewis structure, a condensed formula, or none of these show all the bonds. Well, let's think back. A molecular formula is like saying H2O. It tells you how many of each of the elements. It does not show the bonds. So first one, no. Lewis structure. Lewis structure is your correct answer. It shows all of the bonds. It shows which atoms are attached to one another. The last one is a condensed formula. Condensed is when you will show the carbon, say, but you would say that on that carbon there's 3 hydrogens, but you don't show each of the hydrogens or the bond for each of the hydrogens. So it gives you the idea of the general shape, but you have to understand that the hydrogens are surrounding each of those carbons. So correct answer for this particular problem, Lewis structure. All right, last question for this chapter. Life and living beings make use of which type of compounds? Ionic compounds, organic compounds, covalent compounds, or all of the above? Well, let's do a quick review. Ionic is between a metal and a nonmetal, so sodium chloride. Organic is a carbon-based compound, such as propane or methane. Covalent are between 2 nonmetals, so sulfur dioxide, something like that. And it turns out for a living person or a living thing that you actually have to have all of these types of compounds in your body. If you remember back to the very first story I told in class, it was about some babies who had ingested some salt and it threw off their electrolytic balance. You do have to have some ionic compounds in your body. You have to have some covalent compounds, and of course you have some organic. Some students will want to say it's just organic because, that's chemistry of life. No, in your body, it actually requires all different types of compounds. And that is the conclusion of chapter 3. Good luck on your test.